We've looked at single sample testing. Now we're going to move to two sample testing. This is the same data we've used before. It's the Montgomery County, Maryland traffic citation data. And we want to ask questions about two groups instead of one group like in the last lab. So we'll start with a question about proportions. Female versus male drivers and warnings versus citations. Then we're going to sort down to some particular data, so we'll do what we've done before. Click a single cell in the data, insert a pivot table. We're going to restrict ourselves to the first district, Rockville. And we're going to look at violation type and male versus female. And just to make it a little more interesting, we're also going to look at, where is it? Unmarked patrol cars. There weren't a lot, but it was 189. And our question is, in this group, is this evidence that females are more likely than males to get a warning? Well, to do that, we first have to come up with hypotheses. So our question is a broad question. Are females more likely? Well, here's how we'd put it in formal terms. The research hypothesis, our questions, are females more likely than males to get a warning, versus the null hypothesis, there's nothing going on. This is different than previous ones because we'd have the proportion equal to a specific number or greater than, less than, or not equal to the same specific number. But now we have two groups. It's a two sample or two population test comparing the female to the male population. To complete the test, it's the same template we've been using. We've already used a single sample. Let's look at the two sample. It asks for a lot more information. We've got the null hypothesis. The two proportions are equal. We don't put the alternative hypothesis or the research hypothesis actually in this sheet. But we have places for our input, and there's not a lot of input. We're going to stick with the 5% level of significance for alpha, so I won't change that. But we have to get, for each group, we'll let sample 1 be the females, sample 2 be the males. How many were there, and how many successes were there? Well, how many got warnings? Males, how many were there, and how many got warnings? Let's look back at the data. So females, there were a total of 67. And 9 of them got warnings. Male, there were 122. And also 9 of them got warnings. Let's look at what this is telling us. The sampling distribution is a little different than the other one because this is the sampling distribution of the difference in these two statistics if the null hypothesis is true. If at a population level there's no difference between the incidence of warnings versus citations for females and males, and then we went out and took samples of these sizes and looked at the difference in these two numbers, which in this case is 6.1%, this would be the distribution of all possible results. It wouldn't always be 0 because there'd be sampling variability. In this case, we landed right here at about 6.1% for the difference. So we go into the p-values. This was a one-tailed test. Go back and look at the hypotheses. We hypothesized whether or not females were more likely. That makes it a single tail. So in the template, we look at this p-value, not the other one. 8.7%. Well, at the 5% level of significance, that's not small enough. So we could take these results copy them, so we have the actual numbers over here, but we still need to state a conclusion. Remember, 8.7% is bigger than 5%. So our formal conclusion, with a p-value of 8.7%, we fail to reject the null hypothesis. At the 5% level of significance, the sample does not provide evidence that the females are more likely than males to receive a warning when pulled over by an unmarked patrol car in the Rockville district. Let's look at a different question. Let's look at, the age of vehicles. Let's stick with the male-female. There's a lot of things we could look at in here. So I'm going to go back to all of the agencies. Just put them all in. I'm going to go back to all types of arrest. All types of violations. So there's an awful lot of male, female, and some unknown values in here. If I want to look at the make of vehicles, there are lots of options. If you look at this, it's interesting data. It's not real clean data. We've seen some of this before looking at the set. Different ways of spelling Acura. We're going to look at Mercedes vehicles just because that was interesting to look at. And we'll slide on down and you'll see there's many different ways that the officers have entered Mercedes into the database. Merc-Benz, Mercedes, Mercury, and there's other ones down here spelled differently. Mercy-Benz, Merced. We're going to go with the regular traditional spelling of Mercedes, which I need to get to. There we go. That one. Now I've only got 419 cars in the entire state. So I've got 134 females who got pulled over driving Mercedes and 285 males. But I want to know about the age of their vehicles. So I'm going to do two things with age. I'm going to drag it in here and turn it from sum to average. One decimal place is plenty on this. And those sound pretty big, but if you go back to our last lab, you got to remember that there are age values that aren't valid. I didn't worry about these when I was asking proportion questions, but in this case, I'm actually analyzing the age variable. So I need to wipe out all the 999-year-old cars because that was a code in this data set for no valid value. That looks a little more realistic for the ages. So I've got how many, I've got the mean, I also need the standard deviation. I can drag age down to the sum values again, but I don't want to sum it. I want to change that one to the standard deviation. Again, a single decimal place will be plenty. Now I've got everything I need. On my hypotheses, I should jump to. There we go. I just kind of said, is there a difference in the mean age? That means I have a two-tailed research hypothesis. I'm not looking for ahead of time, are the males driving older cars? Are the males driving newer cars? I just kind of wondered, is there a difference? So my null hypothesis, of course, there's no difference. My research or alternative hypothesis is that they're different, no particular direction. There's my summary statistics. I'll go back to my template. This is a test for means, not a test for proportions, because I'm dealing with age, not category. Now it's a t-distribution instead of a z-distribution. We've dealt with that before. It's the t-statistic based on, there we go, t-statistic based on the fact that if the null hypothesis is true, these differences would follow this t-distribution with, in this case, 98 degrees of freedom, but I haven't put the data in for this particular test. Slide this down, and we'll let sample 1 again be female. So the information on the Mercedes driven by females. Sample 2 will be male, the information on the Mercedes driven by males. So females have a mean age of 7.7. They were a total of 52 of them, and they have a standard deviation of 5.7. Males have a mean of 9.4. There are 284 of them, and the standard deviation is 6.9. So again, if the null hypothesis is true and there's no difference in the means of the Mercedes driven by men and women, we would have this distribution of all possible test statistics. Well, I'm out here. That looks pretty far out there. And of course, the p-value tells us that. There's 0.43% below that. If I'm looking at a two-tailed test, I double that because it'd be this direction or that direction, the p-value meaning what's the probability I get sample values this far apart or further if the null hypothesis were true. So if this blue graph were true, what's the probability I'd land this far from the center or further? Two-tailed means either direction. So there's my p-value. I'm going to, again, just because I can, copy it this way, rather than try to just type that information over into here. So I'm going to paste special, paste as an enhanced meta file. There we go. And my conclusion, this p-value, and it's the two-tailed one again, is quite a bit smaller than a 5% alpha. So with a p-value of 0.86%, less than 1%, we reject the null hypothesis. The sample provides evidence that the mean age of Mercedes vehicles driven by females differs from those driven by males. And we got two different conclusions. One of these was a fail to reject. We failed to reject a claim that women were more likely to get a warning, although in our sample, the percentage of women getting a warning was 13% versus 7.5% for the men. That wasn't enough to be statistically significant. We said, there's an 8.7% chance that we would randomly get a difference that big or bigger, so we failed to reject the null hypothesis. The question is, are we right? So it's a good time to review errors. In the real world, the null hypothesis is either true or false. We don't necessarily know, but it's true or false. And then when we're done, we either reject it or we fail to reject it. In this case, we failed to reject the null hypothesis. So are we right? We actually don't know. If the null hypothesis is true and there's no difference in the proportion of males and females who get warnings, then we made a good decision. But it's possible that there actually is a difference and our test simply wasn't sensitive or, in statistical terms, powerful to catch that difference. And we don't really know. You never know for sure if you made a right decision. So we might have made a type 1 error, or we might be correct. For the second one, we did reject the null hypothesis. We said this is a really small chance, very small probability that if men and women getting pulled over in Mercedes were driving equally old vehicles, very small chance that we would see guys driving vehicles that by a sample statistic looked that much older. Same thing though, now we're here. We did reject the null hypothesis. So if it's false, if there really is a difference, we're fine. But what if the null hypothesis is true? There actually is no difference, and our result was just an unusual random outcome. That could have happened, and we would have committed a type 1 error. That doesn't mean we did something wrong statistically, and we don't actually know. But you should always keep in the back of your head that when you make a conclusion in statistics, you aren't sure that you're right. You just have the data that you have. And the data gives you evidence or it doesn't give you evidence. It doesn't make a conclusive decision. So that's the process of how to do two sample tests for proportions or for means. You've got the template available. You've got the data available. So you ought to be able to go on and do the next lab.